Dear all, I welcome you all to the seventh lecture of the Professor Rajani Prasanna Endowment lecture series on climate change and its impact on public health. We wholeheartedly thank Professor Rajani Prasanna, philanthropist and art historian, for this endowment and its focus towards climate improvement for the next generation. We also thank our chief patron, Mr. D.A. Prasanna, the managing partner at Akinova Life Sciences LLP, ex-chairman and founder at Akron Akinova and founder at Manipal Akinoma Limited, for his philanthropic work and endowment towards public health research and establishment of the Prasanna School of Public Health, MAHE Manipal. Now I'd like to introduce and welcome Dr. Imad El Haddad, who is a group head at Molecular Cluster and Particle Processes Research Lab Head, that is, in Laboratory of Atmospheric Chemistry at the Paul Scherrer Institute, Switzerland. Dr. Imad's goal is to comprehend and quantify the process by which anthropogenic emissions have altered the composition and level of atmospheric pollutants, as well as the effects of these changes on Earth's climate and public health. He has publications in numerous reputable journals such as Environmental Science, Atmospherics, Nature Chemistry, and Atmospheric Measurement Techniques. His mapping climate-relevant aerosols across Arctic. Dr. Imad worked alongside an international team of researchers led by then PhD student Varios Muchos under the supervision of École Polytechnique Fédérale de Lausanne and tenured track assistant professor Dr. Julia Schmel. Over several years, they studied the chemical composition and origin of aerosols collected from 8 research stations across the Arctic, providing unique insights to help researchers better understand climate change in the Arctic and design effective pollution mitigation measures. I'd now like to introduce and welcome our moderator, Dr. Satheesh MK, who is an adjunct professor at the Department of Atomic and Molecular Physics, MAHE Manipal. Dr. Satheesh has over 60 publications, which includes those published under the subject of climate and air particle pollution. His paper on exacerbation of fatality rates induced by poor air quality due to open mass funeral fire cremation during the second wave of COVID-19 has been instrumental in setting discussions for policy briefs during COVID-19. His previous affiliations include Research Director at the Department of Atmospheric Sciences at Kannur University, India. His notable publications include Integrated Process Analysis Retrieval of Changes in Ground Level Ozone and Fine Particulate Matter during the COVID-19 outbreak in the coastal city of Kannur, India, where the community multi-scale air quality model was applied to evaluate the air quality in the coastal city of Kannur during the 2020 COVID-19 lockdown. His paper, Variations in Mixing States of Organic Aerosol Composition and Formation of Secondary Organic Aerosol at Background Region. Another paper, Potential Link between Compromised Air Quality and Transmission of the Novel Coronavirus in the Affected Areas, are among other papers. Now we will proceed with the lecture. The presentation will be from 30 to 40 minutes of presentation, followed by 15 to 20 minutes of Q&A, question and answer session, moderated by Professor Dr. M.K. Satheesh.
Yeah, thanks for the introduction. I will present in this climate change and its impact on public health. I'll present a presentation that will be focused much more on sources of air pollution and its impact on health and its impact on the environment. So let's start. So the mission of my group, but also our lab, is to understand the emissions and the processes that determine the atmospheric chemical composition and how our emissions affect or impact the our climate and health. Our mission serves 4 of the United Nations Sustainable Development Goals. Most of what we work on are aerosols. So these are tiny particles suspended in the air. Their size range from some nanometers to some micron. So for example, from a DNA size to the pollen size. In 1 cubic centimeter. So 1 cube of sugar, you may find thousands of particles within a range between 10 in, for example, in the Arctic to 100,000, for example, in India. These particles can be directly emitted from natural emissions, like, for example, desert dust, sea salt, pollen, or even anthropogenic emissions like soot particles. These are the particles that make the building black. But these particles can be also called secondary. These are formed via reactions in the atmosphere of what we will call precursors. These precursors can be inorganic, like, for example, sulfate. So, for example, industries would emit SO2, cars will emit NOx, and these gases can react with OH radicals to form sulfuric acid and nitric acid, which after neutralization will end up in the particles phase. Another part is called organic, which is one of the main fractions um, of the aerosols. Part of it is directly emitted, like, for example, from a biomass burning, but another part is also formed through the reactions in the atmosphere, and it's called secondary organic aerosols. The organic aerosol, we will focus on that because this is one of the most complex fractions of the aerosol. It's formed or it comprises millions of molecules, and our job is to measure some of these molecules and then determine where does these particles come from. Are they primary? Are they secondary? Are they formed in the atmosphere? And how these particles affect our health. So we are interested in aerosols because they impact our climate. They do so either directly by interacting or by scattering and absorbing lights, or by forming cloud droplets. Because without aerosols, we don't have clouds. So clouds and cloud so clouds need aerosols to form, and aerosols change the microphysics of clouds, and then they they result in a net cooling of the atmosphere, unlike the greenhouse gases. Aerosols can also affect our health. The total death toll of air pollution, especially from aerosols, is around 10 million deaths per year. The estimates range between 5 and 10 million, depending on the method used. This is basically equal to the total corona death toll over the past 3 years of 6 million deaths in total. And we rarely speak about this problem. That's a major societal problem. Um, with that, the air pollution is ranked the fifth risk of death worldwide. To study aerosols and their effect on climate and health, we start by developing instrumentations which would look into the composition of these particles and the molecules that form them. We can look at these molecules in the gas before they form the particle, or we can look at these molecules in the particle directly. We use these instrumentations either in the lab to study the different emissions, or in the field in different places, in various places, from polluted areas, like, for example, in Delhi, to like really pristine areas like the Alps or the Arctic. Results that come from the field and from the lab are afterwards integrated into models where we estimate the distribution of pollution around, especially Europe. Then after that, we can estimate what are the impacts of aerosols or from different processes on our health and on our climate. What our lab is really known to do is also that we maintain different stations within the ACTRIS consortium and GAW, so it's a Global Aerosol Watch, where we actually watch the evolution of aerosols since more than 30 years right now. One of the main sites that we operate is at Jungfraujoch. This is how it looks like. This is at the Swiss Alp at 3,500 meters, where we observe the particle scattering. This is the first plot, the particle absorption. This is the second plot, and the particle number concentration. And with that, we can now estimate trends, different trends in aerosols. Like, for example, if we look at the first one, you can see that the first in the 90s, the concentration of scattering aerosol was much higher than afterwards, and and this decrease is due to the decrease in sulfate after the fuels were purified and sulfur was removed from fuel. The same we can observe for black carbon. So, for example, and absorbing aerosols. For example, over the past 10 years, we have a decrease of 3% per year of the concentration of absorbing aerosols. So with that, we can actually estimate the effects of mitigation strategies on the concentration of aerosols and how that will affect our health and how that will affect our climate. This is at a pristine area, but the the ACTRIS monitoring stations are all over Europe, where we operate also something that is called an ACSM. So ACSM is an aerosol chemical mass speciation monitor that will go and look into the composition of the aerosol in real time over long periods of time. Here we have harmonized the measurements and the source apportionment at 22 sites within Europe. And you can imagine how much collaborations that will involve, because every country has its own research station, and also the university or institutes that deal with these measurements. So we have coordinated all of it was a really a big effort to coordinate all of these measurements and the data analysis from these measurements. But the result, it was really worth it. The result is beautiful, and with that we can now map the aerosol in Europe. We know that most of here green is, and this will be for afterwards, green is always organic, black is black carbon or soot, and then the other colors are inorganics. And as you can see all over Europe, whether it's a site that is really polluted, like here in Poland, or sites without pollution, like for example here in Sweden or Norway, most of the aerosol, regardless the site, is actually organic. And this organic is mostly secondary. So it comes from reactions in the atmosphere from precursors that will be oxidized and then will go directly to the particle phase. So with that, we know more or less what is the composition of our aerosol around Europe. Now, if we move a bit away from Europe to this circle here, where most of the population of the world live, we have two really big projects, one in China, one in India, supported by the DETSA, so that's the Swiss Bureau for Development and Communication, from which I will present a bit of results. But let's start a bit from developments or analytical developments. This is a method we have developed 10 years ago, where we take filters from different parts of the world. We extract them, we then rearealize them, and then send them to the mass spectrometer. This is more or less the same mass spectrometer as I've presented before. Then what we can obtain from this is fragmentation patterns indicating the composition of the organics. From that, we can apply some machine learning techniques to get into the composition and the, uh, the sources of this organic aerosol. Now, the advantage of this technique over the techniques that we have been using online before is that it extends the spatial and temperature resolution of the aerosol mass spectrometer. We can measure in inaccessible locations, and I will present a bit some results from the Arctic. We can investigate some special events like pollution events or haze events, and then we can also access some matrices, so like for example, some coarse particles that we cannot access with regular instrumentation. So with that, we have right now analyzed more than 15,000 samples from more than 50 locations worldwide, published 17 publications with 2 in Nature, 1 in Nature Geoscience, and generated more than 5 million Swiss francs or 5 million euros um, in project funds. And we can obtain results similar to that, where we can map different places around the world and then know the composition of the aerosol at these different places. One of the first application was in China, where we have identified for the first time that even under severe haze conditions, where we have so much pollution, so much direct emissions, the main contributor to the organic aerosol or the aerosol in total was secondary processes. So these are reactions happening in the atmosphere that we thought were slow, but we could show that these happen very quickly and that most of the aerosol is actually secondary. The primary aerosol in China, especially in Beijing, comes from coal and combustion, from biomass burning, and in some location from dust, especially at locations that are not far away from the Gobi Desert. This work had been published in Nature, and in that work we have analyzed one of the main or major haze events over the past 15 years that occurred in January 2030. Now, with more advanced instrumentation, we can start to look into the molecules that compose the different fractions. So before, or when I talked before, we could see the fragments and the bulk composition of the aerosol. These are very useful information. We can distinguish between hydrocarbons and oxygenated fragments. However, we don't know the molecules that form this aerosol. But we have developed new methods to be able to look into single molecules inside these aerosols. This is just one example from one of the sources in China. And this is a more recent analysis we've done where we have shown that in Beijing, there are two main or major aerosol sources. One is age-transported biomass burning, the first one, and the second one is organic aerosol or secondary organic aerosol formed in the aqueous phase. And we could see the increase of this at when we have higher relative humidity, and one can have a look at how complex this aerosol is with every marker denoting one compound. And this is mainly observed when the air masses go over regions where we have a lot of NOx. This NOx comes from cars, but then, as I said, it oxidizes in the atmosphere. It forms nitric acid. Nitric acid co-condense on the aerosol together with water, and then offering a reactive vessel for the organics into which the organics can react, forming this this blue fraction here. So all of this we couldn't do without looking at what are the molecule composing the different fractions. Now from China to India, and India is a very interesting place for many reasons, but one of the reasons we are interested in is the unfortunately the high pollution that is there. If you look at the composition of the aerosol, the total aerosol, you can see that several things. First, that the concentrations are around 350 microgram per cubic meter. And that's the average over the entire December, January. So you have some days with peak concentrations exceeding 1,000 microgram per cubic meter. Compared to Europe, we rarely see anything, I mean, depending where and location, so on and so forth. But at least in Switzerland, the concentrations are lower than 35 microgram per cubic meter. So at least factor 10, if not 50, lower than the concentrations that are in Delhi. Another interesting observation that I haven't spoken about before, but that's because it's very particular to Delhi, is the observation of this pink here, which is actually chlorine. Chloride is actually formed from chlorhydric acid in the atmosphere, and the sources of this hydrochloric acid are still not known in Delhi. We don't know from where does it come from, but we expect some specific types of industries that emits hydrochloric acid that co-condense on particles together with water. This is a process that we've never seen anywhere else in the world. India was the first place where we see this. But then if you look at the green, it's still one of the, this is the organics, it's still one of the main components. And if we look at the sources of these organics on the right-hand side, we can see that most of it is secondary with a lot of primary biomass burning and traffic. If we look at more into details, we can see that mainly in the daytime you have secondary organics from biomass burning, from traffic, and from different urban emissions. But in the night, it's mainly primary emissions from residential biomass burning, from open biomass burning, and from traffic. Actually, in the residential biomass burning, we could also see, because it has its own signature, part of it is actually from cow dung combustion. From the open biomass burning, it's mainly from land clearing, and it peaks rather not in winter, but rather before and after winter, during the land clearing seasons. Now, I spoke a lot about polluted areas, but our pollution also can travel far and reaches pristine areas. And we wanted to know how much our pollution can affect the Arctic. Why the Arctic? Because the Arctic is warming 3 times faster than the rest of the globe. And aerosols play a major role in this warming by forming low-level clouds. Aerosol levels will also increase with melting and increasing human activities. And also we could clearly see over the past several years what we call warm mass intrusions. So these are warm masses that come uh, from Europe, from southern areas, that actually can intrude the Arctic atmosphere, and then increase the concentration by 10 of aerosols and pollutants by factor 10 for a brief moment of time. But these are first warm, so they warm the Arctic, but also some of these pollution persist and can warm even more the Arctic. So what we wanted to know is, what is the composition of the aerosol right now, so that we can predict afterwards with the global warming how the composition will be. But for that, we have analyzed 350 samples from 8 sites covering 6 countries and 10 cumulative years. As you can see, the sites are well spread in the Arctic Circle. And we have, for some of the sites, around 3 years of data. And we have analyzed this with several mass spectrometers with different analytical techniques to get an overview of the aerosol in the Arctic. So there, I will be brief for our findings. So what we found is that in winter, most of the aerosol is actually anthropogenic, coming from gas flaring, and that's mainly from Russia, and from secondary aerosols transported from Europe during the Arctic haze. And while in summer, most of the aerosol is actually natural, either from marine emissions from the Arctic Ocean, or from the boreal biome, especially from Russia. So that's basically either primary biological particles. It's not pollen, but it's basically plant debris and spores that come from the boreal biome, or secondary organic aerosol, biogenic secondary organic aerosol. So these are plant volatiles that go into the atmosphere, get oxidized, and then will be transported. The aerosol that is formed will be transported to the Arctic. In general, the natural and the anthropogenic right now, the natural and the anthropogenic contributions are more or less equal right now, and it depends on which side do we consider. But in general, this is the main picture that we can uh, derive about in the Arctic. Besides looking into the composition of the aerosol in the field, we also look at the composition of the aerosol in the lab from specific sources, like for example biomass burning, cooking, jet engines, or mobile or like trucks and vehicles. What we have focused a lot on recently is solid fuel burning from that represent some of the processes happening in India, like for example cow dung burning, straw burning, plastic burning, and then wood burning. We use these results to understand our ambient observations. So we look at the aerosol in the chamber or in our labs, and then we compare that directly to the ambient. Or we can also use these emission factors and parameterizations to feed into our models. And I will present an example here. So the example I will present is actually from focused on biomass burning. So biomass burning, when you burn wood, you would form a lot of particles, but these particles contribute only five. This is here called POA. Is actually contribute 5% to the total carbon budget of the emissions. So it's only 5%. So all the smoke you've seen when you light a fire, that's only 5% of the total carbon budget. The remaining is actually in the gas phase. Part of it are just small molecule like acetic acid. So acetic acid is what you find in the vinegar, um, and other small volatiles that will not do much. But the other part, which is also around 50%, is actually secondary organic aerosol precursors. So these are volatile organic compounds that can be oxidized, and after oxidation will give us secondary organic aerosols. These we can distinguish several types. Some are, we call them furans. Furans are actually the product of decomposition of cellulose. We have oxygenated aromatics. This is more or less, I mean, like cresol, for example, or phenol. This is what gives the wood smoke its smell. And this comes from the fragmentation or the pyrolysis of lignin. So this is the other polymer in wood. And then one can also find aromatics and unsaturated like unsaturated hydrocarbons that come directly from incomplete combustion. Now this is the primary emissions. When we when we turn on the light and then have some oxidants will form, and then in basically 2-3 hours time, most of the or half of the gas phase will be consumed. When half of the gas phase is consumed, you can clearly see at the same time the formation of particles. These are what we call secondary organic aerosols. We compare how much we form particles to how much we consume um, gases, and then we derive the yield of secondary organic aerosol, which afterwards we can put into the models to be able to represent these emissions in, for example, in Europe. Our modeling domain is, as I said, is Europe, and we compare the modeling results to measurements at several sites that are obtained using a mass spectrometer. Here is a comparison for 11 sites. Uh, the the bar that is black is actually the measurements. The other bar is actually the model. And as you can see, the model gets really well side-to-side differences. It gets the concentration within less than 30% error. Um, it also gets the composition, and it tells us that 70% of the aerosol is actually secondary and 30% is primary, composed of biomass burning and traffic. The model does not only get well the average values, it also gets well the temporal variability. And with these models, we can derive a global picture, or at least a European picture, of the composition of the aerosol. And what we can see is that the main contributor is secondary biomass burning emissions and primary biomass burning emissions, especially in winter, while in summer, most of the what contributes most is actually biogenic emissions. So these are plant volatiles. To finish my talk, I have promised to talk about the toxicity. I mean, we talked a lot about the sources of the aerosols. We define them. We can derive these sources. We can understand these sources in different places of the world. Their impact in the Arctic and their impact in India, China, so on and so forth. And then how do we model them from chamber data? But we've not talked about their toxicity. Now, most of the toxicity or all the toxicity analysis is based on the total aerosol mass. So this is here on the x-axis, it's called ambient PM 2.5 mass in microgram per cubic meter. And this is the cause-specific mortality increase as a function of ambient PM 2.5 mass. The main reasons for or causes are actually stroke, then heart disease, then respiratory infections and lung cancer. So these are the main reasons that cause the mortality from pollution. Now, but all of these relationships are derived as a function of ambient PM 2.5 mass. However, its toxicity is a function of its chemical composition, and one of the main ways the aerosol affect us is by something that's called reactive oxygen species. These reactive oxygen species can oxidize our vitamins or our antioxidants in our lungs, which will cause repeated inflammation, which afterwards cause chronic ailment, which afterwards cause the observed death. So what we wanted to know to answer is whether the ambient PM2.5 and ROS, whether these two properties, do they have the same sources or do they have completely different sources? We've done that in a big project where we have modeled the aerosol mass in Europe and then the ROS levels in also in Europe. And as you can see, there is some correlation between the two, where you could see, for example, the Po Valley, you can see Paris, and you can see Madrid. So we could clearly see the correlation of hotspots between ROS and aerosol mass. However, aerosol mass is a bit more homogeneous, where you can see less abrupt changes between capital cities and the rest. Now, these are the levels. If we now start to look into the sources, we can see that the main sources are of aerosol mass and ROS are very different. The aerosol mass, at least in Europe, mainly comes from dust and from inorganic ions, so that's sulfate, nitrate, and ammonium, while ROS comes from anthropogenic combustion and from vehicular wear. So if we now start to reduce only aerosol mass, this may not be as effective in reducing aerosol ROS and aerosol health effects. So now, to have a look into some perspective, we continue working a lot on aerosol sources. We model them to get exposure, and we start right now big, really large interdisciplinary collaborations with epidemiologists to really know the effect of single sources on our health. For that, we have collected throughout the EU. Every dot here is one site. So we have collected throughout the EU more than 500,000 data points of aerosol composition to be able to generate models that will capture the exposure or personalized exposures to aerosol sources, so to single aerosol sources. At the same time, we work with medical doctors. Here is an example where we were measuring with our instrumentation COVID patients to see whether we can distinguish COVID from breath analysis. That's just one example. And with that, we can directly engage with the public. We also work with urban scientists and with climate scientists to see the influence of future urban greening and future renewable energy and global warming on our air pollution, and to really predict how air pollution will be, and how air pollution related mortality will be in the future with the future climate change and with future global changes in our cities. With that, I would like to thank you for your attention.
Thank you, Dr. Rahul, for giving me an opportunity for sharing this session. And Dr. Imad, wonderful presentation, because you have discussed a burning issue which is being addressed all over the world. All right. Now, I have a few questions in the chat box. The first one is D'Souza Viola. How do natural sources of particulate pollution, such as dust storms and wildfires, compare to human-caused sources in terms of impact on climate change and public health?
Yeah, I mean, we know that we have increased a lot the aerosol particle number, and that's one of the main ways we impact our climate. So basically, by increasing sulfur emissions, we have and by burning ourselves also some like fossil fuels, we have increased by a lot the particle number, and therefore we have changed the cloud properties significantly. So I would say that our emissions have probably tripled or quadrupled the particle number concentration. Therefore, they actually compared to the natural emissions, they are much like they influence directly or more the climate right now. As for our health, in cities, I mean, it depends where. In Switzerland, we start to have levels that are mainly affected, or aerosols that are mainly affected by natural emissions, because anthropogenic emissions are really have really went down. But in places like in China or India or even some places in Eastern Europe, the levels of anthropogenic emissions remain very, very high, probably factor 10 to 100 more than biogenic or natural emissions. So I would say that we, by far for our health, anthropogenic emissions still win.
Okay. Now, another same scholar asked another question. How do advances in technology, such as electric vehicles and clean energy, impact particulate pollution and public health?
Electric cars, at least, electric cars will remove the emission part, which is well, like the exhaust emission part, which is very good. But one part that will not be removed is actually the mechanical, the one that is generated mechanically. So this is what we call vehicular wear or brake wear. And brake wear is one of the sources that we have identified to be one of the most toxic ones, because it contains heavy metals that can directly be deposited on our lungs and then cause a lot of harm. Um, but in general, uh, what we can act on is, for example, removing copper and other metals from these braking pads. So in general, renewable energy and electric cars will give us better air quality. Now, one exception is biomass burning. Biomass is considered to be a renewable energy source. However, it is known to be one of the dirtiest sources, especially when it's burned in houses. Now, there are ways to counter that. So, for example, some burners don't use directly wood logs, but they use pellets, and these are known to emit much less organic aerosols and organic vapors.
Okay.
So the combustion is more complete.
Again, another one is, does seasonal weather such as monsoon, spring, winter have a direct effect on environmental aerosol? And how much effect does garbage dump release of methane due to the food waste lead to aerosol increase?
So the question is how much the
It is
methane.
seasonal change of aerosols. For example, if you have measure in winter, summer, and the spring, is there any concentration changes, and whether it is attributed to the garbage waste?
Yeah. So basically, there's a clear seasonal variability in aerosol in India. The concentration in winter are 10 times higher than those in summer. So basically in winter you have 400 microgram per cubic meter, and summer it's like, I don't know, 60, 70 microgram per cubic meter. And that's because the boundary layer height is much lower. So there's no dilution. So most of the pollution remains and is not diluted elsewhere. So there's a big seasonal variability between summer and winter. Now, like waste burning, this is what we have identified as one of the factors for, we called it open burning. And it is true, it's like probably 25% or 30% of the aerosol is from waste burning. Now, I'm not so sure if that's from big incinerations or if that's just on a local at the local level. So small, like people just burning their plastic or other garbage.
Okay. Now we don't have much of a time because 5 minutes is there, and I have only a single question. You have already mentioned the identification of hydrochloric acid in Delhi. I think it is hydrochloric acid in Delhi, right?
Mm-hmm.
And I think it is mainly formed due to the waste burning and plastic and waste burning, because the point is that this chlorine combines with ammonia to form ammonium chloride, definitely.
That's true.
Right? And this ammonium chloride is an element which can absorb water, right? Probably.
Mm-hmm.
Yeah.
Mm-hmm.
That reduces the visibility. Is it correct? I don't know much of it, but from your experience.
No, all of that is correct. I mean, we do understand perfectly well the formation of ammonium chloride, and it co-condenses with water. So it actually it condenses and then it absorbs water. More it absorbs water, more it condenses. So it's like it's a snowball effect.
Yeah.
And we perfectly can model thermodynamically how does that form.
Yeah.
The main problem, and it's directly formed in the night when the temperature goes down, the relative humidity goes up, and you could clearly see ammonium chloride going up in the night.
Yeah.
So we perfectly understand even which size of the particles we have it. Now, the main problem is that we're not sure about, we have some suspicions, but we're not sure about the sources of chlorhydric acid or hydrochloric acid, sorry. It can be, as you said, from plastic burning, but you need really a lot of chloride because, I mean, its concentration in the atmosphere, or like ammonium chloride concentration in the atmosphere, are as much as sometimes as the entire organic aerosol, you know, so organic aerosol from biomass burning. So as much as you have from biomass burning, so that means that people are burning plastic as much as they're burning biomass. So the concentration are insane. So that's why we're still puzzled about the main source of it.
Yeah. Okay. So I think one more question is there, but I don't know whether we can finish it off. The question is, do you think international agreements and cooperation can play a role in addressing particulate pollution and its impact on climate change? For example, platforms such as United Nations Climate Change Conference or Conference of the Parties of the UNFCCC. I think this needs an extensive answer, but we don't have time. Anyway, Dr. Imad, a very good talk, extensive one, and you have addressed you have made a concise and a brief account of your studies and your instrumentation and your models and how your models can deploy the nationwide increase. And I am very surprised Barcelona has the highest emission inventory in your result. Okay, so I think, and all the very best for your future endeavor. So I am handing over to Dr. Rahul.
Thank you, Ben.
Thank you, everyone. Again, I would like to thank Dr. Imad for the presentation and Dr. Satheesh sir. I know that Dr. Satheesh sir had a lot more questions in his mind, but given the time constraint, we'll just keep. I'd also like to thank Professor Rajani Prasanna Madam and our Chief Patron, Mr. D.A. Prasanna Sir, the contributions towards climate change, setting up the betterment and value knowledge for the next generation, and also towards setting up this Prasanna School of Public Health. Thank you all students for joining us. I'd like to thank Ms. Viola, our Student Research Forum Coordinator, and Ms. Alisa, who's a sub-editor, for joining us. Thank you all. Thank you so much.
Thank you.